guys, this video is all about how we can predict the boiling point of substance just by knowing what type of bonding it contains. My students find this really tricky, so we're going to go through it step by step and hopefully simplify it a little bit more for you. The way we're going to do this today is in a table. So what we've got here are 4 columns, which are all for the different types of bonding that we're going to go through today. And for each of them, we're going to do an example and then go through how the bonding leads us to the boiling point. So let's get started with ionic bonding first. The example of ionic bonding that we normally use is sodium chloride or table salt. So whenever you get any substance that's ionic, I want you to think about table salt because that will give you some precious information that you can apply to any other ionic substance. In this box underneath, I'm going to draw out the structure of it. From a previous video, you'll know that ionic compounds are arranged in a 3-dimensional lattice, and that giant lattice is made up of oppositely charged ions that have strong electrostatic attraction between them. When we boil an ionic substance, what we're doing is we're breaking apart all of those oppositely charged ions. And because they're held together really strongly, that means that their melting points are really high. So ionic substances have really high melting points because of their strong electrostatic attraction between those oppositely charged ions. The next type of structure we're going to look at today is a giant covalent structure, which are made up of many covalent bonds. And the example that we're going to look at is diamond, but it could just as easily be graphite. It doesn't matter which ones you pick. What we've got here is we've got a structure which is made of many covalent bonds. Now, if I was to melt diamond, what I'd have to do is to break apart all of those covalent bonds. And covalent bonds are really strong. They require a huge amount of energy in order to be broken. So that leads us to having a boiling point that is super high for giant covalent structures. This shouldn't really surprise you because if you think about diamonds, diamonds definitely have a very high boiling point. Simple molecular compounds are quite often the ones that my students struggle with most. So they have also got covalent bonds between them, and examples that you've come across are probably hydrogen, chlorine gas, or water. There are many examples of these that are in your syllabus. The example that I'm going to use to try and explain this is water. So what I've drawn here is water in its liquid form. You can see it's a liquid because all of the water molecules are arranged close together. They're almost touching, but they're not in that regular arrangement that you'd expect from a solid. So the question is, what holds all of these water molecules together? And the answer is something called intermolecular forces. An intermolecular force is the force that holds 2 molecules together. In the same way that international means between nations, intermolecular means between molecules. So what we've got here is intermolecular forces drawn in red here to show you the force between them. What we want to think about is what happens when we boil that liquid water. So if you boil liquid water, what happens is those water molecules get further away from each other, but they're still water. It's still H2O. I'm not breaking up the water. I've still got steam there. So I've drawn the water molecules now really far apart from each other. What that means is that when water or any simple molecular substance boils, what's breaking is the intermolecular forces. They're the things that are being broken in that process. In this case, those intermolecular forces are really weak. They're really weak by comparison to covalent or ionic bonds. They're much more easily broken, which kind of explains why all those things in my examples are gases and liquids, because they're quite easy to break up at room temperature. So simple molecular substances have a low boiling point. Now you may be thinking that they've both got covalent, both giant covalent and simple molecular, but one has a high boiling point and one has a low boiling point. The reason for this is that in diamond or graphite or silicon dioxide, everything is bonded to everything. You don't have any molecules in diamond or graphite. So what that means is it means you have no intermolecular forces, because you can't have intermolecular between molecules when you only really have one big molecule. Let's look at the last type of bonding, metallic bonding. So examples of metals are iron, zinc, copper. You've come across many in the world around you. The structure of a metal is just like the previous video, with my layers of positive metal ions and those delocalized electrons. Now, metals, you probably already know, have a very high melting and boiling point. And the reason for that is exactly the same as in ionic bonding. So the reason is because you've got that strong electrostatic attraction, but this time it's between those positive metal ions and the delocalized electrons. Apologies that this video was a little bit longer than normal, but it was kind of necessary to get all of that key information across. I hope you're feeling a bit more confident in predicting those boiling points. Just make sure that you can definitely identify the type of bonding first, and then you're onto a winner.